For most of your life, electricity has felt permanent. You flip a switch, the lights turn on, your phone charges, your food stays cold, your internet stays alive. It feels automatic, invisible, reliable. So reliable that we don't think about it at all. But that sense of reliability is misleading, because the power grid doesn't actually guarantee electricity. It assumes normal conditions, and increasingly, normal is disappearing. What makes today's power grid dangerous isn't age or neglect or even demand. It's something more subtle. The grid was designed for a world that no longer exists. And the scariest part is this: when it fails, it often fails quietly, long before the lights go out. If you look at old photos of electrical infrastructure from the mid-20th century, one thing stands out. It's simple. Power plants generated electricity, transmission lines carried it, substations distributed it, consumers used it. The system was centralized, predictable, slow to change, but stable. Engineers didn't design it to be clever, they designed it to be robust. Back then, electricity demand followed patterns that barely moved. People woke up, went to work, came home, turned on appliances, went to sleep. The grid rose and fell with human routine, and that predictability was everything. Because electricity is different from most resources. You can't store it easily at scale. You can't pause it. You can't wait for it. At every moment, supply must equal demand. Too little power and systems shut down. Too much power and equipment overheats or destabilizes. The old grid survived because demand changed slowly and everyone knew what to expect. That world is gone. Today's grid is expected to do something it was never built for. It must respond instantly to millions of unpredictable decisions made by machines. Electric vehicles don't charge like light bulbs. They draw huge loads, often all at once. Data centers don't sleep. They spike demand without warning. Solar power doesn't obey schedules. Wind doesn't respect peak hours. And artificial intelligence systems consume power in bursts that didn't exist even 10 years ago. The grid now lives in a state of constant improvisation. But here's the uncomfortable truth. Most of its bones are still old. Transformers installed decades ago are being asked to operate far beyond their intended duty cycles. Transmission corridors built for steady flow now experience rapid reversals. Protection systems designed to isolate simple failures now face cascading complexity. From the outside, electricity still looks smooth. Inside the system, it's under tension. One of the most misunderstood ideas about power grids is failure. People imagine blackouts as dramatic events, a storm, an explosion, a sudden collapse, but that's not how most grid failures begin. They begin with small imbalances. A transformer runs slightly hotter than normal. A line sags just a bit more than expected. A control algorithm reacts a few milliseconds too late. Individually, these are manageable. The danger comes from interaction. Modern grids are tightly coupled systems. Each component depends on many others behaving correctly at the same time. When conditions are stable, this coupling improves efficiency. When conditions change rapidly, it becomes a liability. A single miscalculation doesn't cause a blackout, but it can push the system into a state where recovery becomes difficult. And here's what makes this especially dangerous. These stresses are invisible to the public. Lights stay on, screens stay bright, life feels normal. Until suddenly, it isn't. There's a reason engineers worry more about near misses than disasters. A blackout teaches you what failed. A near miss tells you what almost failed and why it might fail again. And modern grids are experiencing more near misses than ever. Not because engineers are careless, but because the system is being asked to behave in ways it was never designed to handle. Consider frequency stability. Electric grids operate at a precise frequency, usually 50 or 60 hertz. That frequency is a heartbeat. Too slow, and generators fall out of sync. Too fast, and equipment can be damaged. In the past, large spinning generators naturally stabilized this frequency. Their physical inertia resisted sudden changes. Today, many power sources don't spin. Solar panels don't rotate. Batteries don't provide inertia. Power electronics react instantly, but without the natural damping older machines provided. The grid has become faster, but also more fragile. Engineers compensate with software, with sensors, with automation, but software responds to models, and models are only as good as the assumptions behind them. When conditions exceed those assumptions, response becomes guesswork. Another quiet risk lies in efficiency itself. We've optimized the grid to reduce waste, to operate closer to its limits, to extract more value from existing infrastructure. This makes economic sense, but it reduces margin. Old systems were inefficient, but forgiving. They had slack, buffer, room for error. Modern systems are lean. They work beautifully under expected conditions. They struggle under surprise, and surprises are becoming more common. Heat waves increase air conditioning load exactly when power plants are least efficient. Cold snaps stress natural gas supply feeding generators. Wildfires threaten transmission corridors. Storms knock out infrastructure faster than crews can repair it. Each event alone is manageable. Together, they strain a system built on assumptions of rarity. What makes all of this unsettling isn't that engineers don't see it. They do. But large systems don't change quickly. Infrastructure lasts decades. Regulations lag reality. Upgrades are expensive and political. So the grid adapts the only way it can, incrementally. Patching problems, adding layers of control, increasing complexity to manage complexity. This works until it doesn't. Complex systems don't fail gracefully. They fail suddenly after long periods of apparent stability. That's why confidence is dangerous. When everything works, it feels like proof the system is fine. In reality, it may be operating closer to its limits than ever before. This doesn't mean catastrophe is inevitable. It means reliability is no longer automatic. The grid of the past survived because the world changed slowly. The grid of today survives by prediction, and prediction is fragile, especially in a world shaped by climate volatility, digital demand, and machine decision-making. Electricity is still flowing. The lights are still on. But that's not evidence of safety. It's evidence that a very old system is working very hard to appear normal. If there's one thing to take away from this, it's not fear, it's awareness. Modern infrastructure doesn't fail because it's weak. It fails because it's asked to be something it was never designed to be. The power grid wasn't built for this world. It's adapting in real time. And for now, it's holding. But the question isn't whether it works today. It's whether it can keep working as the definition of normal keeps changing.